Now we are going to proceed to a seminar with a couple of props with a real camera, and this is a brand new robot. Let me tell you a couple of things about it. So it has 0 servo motors. As you can tell, there are none. And it has a single camera, so it's a monocular robot. It's not that much of a humanoid shape, but still, it's a robot, and today we're going to work with it. It contains of some plastic, sticky tape, and that's pretty much it. So, jokes aside, this is a mono camera, regular, normal one that you can buy for $15, maybe. And we're going to calibrate it. We're going to measure some distances. We're going to check the intrinsic parameters of this camera, so we're going to play around with it. And the thing is that you can do the same with the real robot, because this camera is clearly set to be apart from the surface. It has certain height, it's inclined, and we're going to measure that angle more or less precisely. And the whole logic of calculating the distances to the objects will remain intact. Let's take a look at the code that I have prepared over here. And the first cell is denoted as capturing images from a mono camera. So what we're going to do is we're going to orient this camera towards me, and I'm going to move around and show this chessboard pattern to the camera. Let's briefly check the code. So it's opening the camera. Strangely, the number of this camera in the system is 0, and it seems like the web camera of the laptop is number 1, but whatever. So we're going to read the frames. Here we have our regular condition for breaking the loop. And here we're going to write down the frame, the current frame, if the spacebar is pressed. And here I have an empty folder by the name of Calib from Calibration. So we're going to save those pictures into this folder. Let's run the code. And now you see the scene as it appears before the processing, so before the lecture is uploaded to YouTube. It looks like this. There's a green background that you are already familiar with. And here is the feed from the web camera. So what can we tell just by looking at it? First of all, it's a Full HD camera. It has high enough resolution, and it has some features of auto adjustment. Let me show my palm, and let's do it like this. So maybe you see some parameters auto adjusting here. But yep, let's calibrate it. And I'm going to show this chessboard pattern in different positions in the frame while pressing the spacebar. Probably you will see the sound. Okay, so it requires some awkward positions, but still I have to cover the whole field. I hope that the detection will work properly while I'm holding this chessboard over here. Please focus up. Okay, so I hope it did indeed focus. Okay, how many photos did we get? 13, 14. Okay, that's kind of enough. It is recommended to use more than that. Well, it doesn't turn off, but okay. We have 14 photos. And let's check them. I'm not sure that they cover the whole field of view properly, but they do it up to a certain extent. So what do we need to do next is we have to proceed to this cell number 3. We are going to obtain the positions of the corners of these cells, of these squares, and they will be used in the camera calibration later. And let's briefly go through this cell number 2. So it's just for recording the video from this single camera or any other camera, basically. For the webcam, it will be the same. So it's just for you. If you would like to record something and then process the video instead of waving the chessboard with one hand and trying to set some parameters with another hand, you can do it easily with the video recorded. And this will be in the code of the seminar, so you can check it if you want to. And we're going to execute this cell number 3. Let's find out if it will be processed correctly. Yep. It's fine. So what do we see here? I think I have to make it bigger. And apart from the color channels being shuffled so that the red becomes blue, the interesting thing here is that over the chessboard pattern over here, you can see the lines of different colors. They mark in poor resolution, but still, they mark basically the corners. And they will be used later in the calibration process. Okay, so let's check that we have them over all the frames. This detection is really robust, and it handled the harsh lighting conditions that could be difficult for other vision pipelines because, well, at some positions like this, the chessboard was halfway in the shadow, but still it's fine. And yeah, I have to say that this chessboard pattern has to be printed on A4 paper. Well, basically any paper, but this specific PDF file is created so that the size of the squares is precisely 2 centimeters, 20 millimeters by 20 millimeters. This is the way in which we can later find out the geometric properties of the objects. So we are using this pattern that was printed on a regular piece of paper, and you can do the same with the normal printer, nothing special. And later in the code, we are going to specify the size of the cell. Well, actually not that much later. It's specified over here. I will show it. So what's going on? First of all, we load the images from the proper folder. We load all of them, and we go through these images. We convert them to grayscale, and after that, we find the corners of this chessboard. It has 7 cells by 7? No, 8. It has 8 cells by 10 cells, and the meaningful, so to say, corners that we can robustly detect are 7 by 9. So we specify precisely that pattern over here. We want to find it, and as a result, we'll get the positions of all of these 63 corners in each of the frames. And here we are creating a grid of the coordinates on this plane. So once again, what is happening? On the line number 12 here, we are specifying the positions of the corners of the chessboard. And the step here is set to be 0.02. What's that? that's 0.02 meters, so it's 2 centimeters. We are specifying here that this whole chessboard pattern is created of the squares 2 by 2 centimeters. That's it. And another thing that we create here is the list of the points that we are going to find in contrast in the real world, in 3D. We store all the data, and later, in the next cell, we have to pass these two lists of data into the function that calibrates the camera. Once again, we have the ideal corners, and we have their positions in 3D taken from the photos, imprecise, noisy data. And this calibrate camera procedure will match them with each other, and with some iteration process, it will give us as an output the calibration data of this camera, and in particular it will be the matrix of intrinsic camera parameters, fx, fy, cx, cy, and the list of the parameters of distortion. So we are going to run this cell and print everything that we have got. Okay, so what do we have here? Here we have the precision up to which the process converged. Here we have the calibration matrix. This is a 3 by 3 matrix. And the majority, well, it will be too much to say majority, but okay, 5 out of 9 values here are zeros, and 4 are non-zeros. Here, 1.41 something something multiplied by 1000, so 1413.75 and so on. It's the focal length in the units of the x-axis. It means that, let me rotate the camera. So there is a photosensitive matrix over there inside the camera, somewhere in the middle. And this value here says that the effective focal length is approximately 1,500 pixels below the surface of the photosensitive matrix. That's the important thing to understand. Second thing here is Fy, focal length in the units of the y-axis. It's different to the Fx, clearly, by 10 pixels. So the focal length measured in the units of the y-axis, in the pixels of y-axis, is different, but it's still close. And those two values tell us the position of the focal point of this camera. And this value over here is the position of the center of the matrix, of the optical center. And what does this remind you of? 9.71, what's that? Okay, first of all, 9.71 multiplied by 100 is 971. And if we multiply it by 2, it will be suspiciously close to the resolution of this camera, which is Full HD 1920. So the center is approximately in the middle, which makes sense. The same goes with the y-axis, because 588 times 2 is nearly 1080. Well, not precisely, of course, but still, it's kind of close. And the rest of the values are zeros, and that makes sense. Here are the distortion coefficients. Here is the list of 5 of them. Those two are responsible for the radial distortion and those for tangential distortion. Also here we have a list of so-called RVEX and TVEX. RVEX are the rotational vectors. Those are the vectors that tell us the rotation of this chessboard pattern in the camera frame. So the rotation that is measured relatively to this camera, taking into account its inclination. And tvects are the translational vectors, so this is pretty much the distance, or it's better to say vector, from here to the chessboard itself. And well, here we are printing only the first 7, but if we print all of them, we will get a single RVEC and a single TVEC for each of the chessboard photographs. If you want to raise a question, how can we set a rotation by a vector? Well, that's done by so-called Rodriguez vector or Rodriguez vector transform or Rodriguez-Euler rotation scheme, something like that. You can Google that, and it's in the OpenCV documentation. We will not talk about that in much of a detail right now, but this rotational vector is the vector that first specifies the direction of the axis around which we are going to rotate the object, and the angle is specified by the magnitude, by the length of the vector. That's pretty much it. Regarding the translation vectors, it's pretty much straightforward. You just translate things by, well, let's take a look here. 29 centimeters along x, minus 28, almost 29 centimeters by y, and 69 centimeters by z. Z-axis is this axis, and it makes sense why is the z-coordinate the biggest one. And now we're going to do the following. We're going to copy these matrices, and we're going to insert them over here instead of the values that we had. Let's do it in a better way. This is the calibration data that I have obtained the previous time I was doing that with the same chessboard pattern and same camera, but I was filming in another circumstances, in another room, and it was just another time. So let's take a look. Here we have actually different value, and it happens so that these processes lead to slightly different calibration. In order to avoid that, you have to take just more photos, and you have to position the chessboard pattern in all the possible positions and orientations all over the field of view. That's what we have to do, and that will make the whole process more reproducible. So I'm going to leave this one here, and here I have to, well, in the code it's A, like in the lectures, and here it will be matrix A. I have to make it numpy array, and I will align it. Don't blame me for using spaces to do that. Okay, and distortion coefficients, it will be an numpy array as well. Okay, so what's going on here? We are going to find the position of the chessboard pattern in the frame given the calibration matrix. After we have obtained the calibration matrix, we really, now using the same chessboard, we can find out its position and orientation. Let this not fool you. We are not doing any magic, so this is still a monocular camera. But the thing is that this pattern is two-dimensional, and we know precisely the size of each cell. So we are properly solving the properly set, formulated mathematical problem. It's fine. I hope it makes sense. We cannot measure the distance to, let's say, objects of arbitrary size, like a ball that we don't know anything about, but we can calculate the distances and orientations of certain objects that we have some information about. So here's the calibration matrix, the intrinsic parameters, the distortion. Here we are stating that we are going to try to find the same chessboard with the same cell size. Here I was trying something with an AV file that I has recorded with the cell number 2 that I was showing previously, the one for recording the videos. And here's a loop. We are doing pretty much the same stuff. And if we have successfully found a chessboard in the frame, we are going to do the following. First of all, we're going to call this function that is solving the problem of mutual correspondence of the points on the chessboard and in the photo. And it will give us the success, well, the flag basically, if it was solved properly, and RVEC and TVEC. Those are the vectors that describe, as I have said previously, the rotation and the translation of a single chessboard in the frame. And after that, well, this massive thing is just writing the result on the frame. And here I have Googled and copy-pasted from this source some code that is translating the RT, the rotation vector, into the Euler angles. And it will be just more interpretable, so to say. Okay, so let's run this code. And really, yeah. Okay, so the output was without commas. Have to do some tedious work. Just a sec. Hope it will work now. Okay, so there are some presses of the quit button that were sitting in the queue. Let's reload the kernel, and yeah, you can see how the camera is trying to auto-adjust for a couple of frames in the beginning. Okay, so now I'm going to move the camera, and I'm going to move the chessboard. Well, no, it has to be fine. Okay, yes, now it's fine. So what do we see here? We have that, we have in the frame, well, in the corner, that the RVEC is this and that, and the TVEC is this and that. And the most interesting part here is the 3 values over here. They are expressed in degrees. And let's find out which one is responsible for what. So I'm going to move this chessboard around, and we will see what is changing. The first one is the inclination, let's say, the rotation in my reference frame around the y-axis, and in the cameras, it's around the x-axis because x is facing this way. Okay, so now we can see that the angle is 27 degrees, and if the chessboard is lying flat on the table, the angle is nearly 54 degrees. We are going to use that later because in order for our pick to R to work, we need this angle, the angle of inclination. So we're going to remember 54. The second angle is this one. and it's the rotation around another axis. And here we can see that if the chessboard is lying flat on the table, this angle is minus 1.3 something. It means that, well, the chessboard is fine, just this assembly of the sticky tape is not precise and the camera is rotated. That's it. And if I'm going to rotate it like this, the angle will become positive. So the last angle that we have to check is this angle. And you can see that it's changing as I rotate the flat chessboard on the table. So that's pretty much it. And you can do that with your robot if you want to. You can set this whole system and attach the chessboard to a wall or something like that. If you want to calibrate, let's say, the vertical inclination or the hip servos. So it's just a convenient way to orient the camera in the world that is not changing, where the chessboard is static. That's it. Now let us proceed to the next cell. We're going to find the distance to an object. Our object is this blue paper cup that we are going first to detect and then to find the distance to. So the first part is to detect. Now let's get back to the seminar number 1, which is about detection by color. And here I'm going to modify this condition if area is greater than, well, whatever, 500. And yeah, that's fine. That's fine. The next thing, the most important one that we have to do is we have to tune the filters. So here are the candidates, and you can easily tell that 500 was too low for the area-based filtering. But still, let's try to tune this filter. And first of all, I'm going to set all the lower thresholds to 0. It's kind of laggy. It responds slower than I would like it to. You know what, maybe we have to increase this waiting time, let's say 280. Should make the situation better. Yep, I have restarted the kernel once again. Hope it works. So let's get to the mask tuning. So I cannot call this the perfect detection, or the perfect functioning of the tuning, but you know what? This is a beautiful chessboard pattern. It appeared just randomly, you see? Okay, and yeah, here you can see the pattern of the keyboard. Okay, here I have set the lower thresholds to 0, and the whole mask is just plain white. And now I'm going to adjust the filter so that only the cup will be visible. Hope it works. By the way, here somewhere you can see the division between the shade and lighted part inside the cup in the mask. Here you can see when I move the cup, it's over here. But those are just the artifacts, just saying. Okay, so let's continue. I would like to tune the filter so that only the blue part of the cup is visible. Oh, it's somewhere here, by the way. And it's in HSV. So I expect it to tune pretty strictly. That's enough, I guess. And here, well, we can excuse ourselves in detecting only the light blue. That's fine. Let's do it like this. Okay. And no way. Too strict. Okay. Well, that's fine. Except for the filtering by area. This cup is bigger than 5,000 pixels, but whatever. So 90, 185. Let me plug them over here. 90, 185. Okay, so I have just copied the HSV thresholds in the today's script, today's Jupyter Notebook. And what else do we have? Well, blurring, bringing it to HSV, obtaining the mask, and that's it. After that, we are analyzing the connected components. And at the instant when we have found one that is big enough, and we can even say that 300, okay, 200, 2,500, we're going to draw a bounding box, and we're going to save the height of the object in pixels, not in centimeters. And we're going to break the loop. So the distance will be calculated using this ratio over here. That is based on the fact that the height and multiplied by the distance is almost a constant in some range of distances. And in order to find the height, well, let's print it. We will at first have to run this whole script and find out the height, and also we have to measure the distance. And now we're going to tune our distance approximator. Nope. Object height. How come? If the area is greater than, really? Let's say that the object height is, let's say, very, very small, okay? When we don't see the object, let's say that we see it at infinity, whatever. So, what do we see here? Here we see the boxes somewhere. Okay. there is a box that is being drawn not properly. It's because of this measuring device being the same color. Okay, so let me at first adjust the threshold area. Let it be 4,000. And another thing is that the drawing here should be slightly changed. Okay, and we can make this bounding box brighter and thicker. Okay. Here's the object. Good. So the height is approximately 240 pixels. And we are going to enter it here. And the distance is 0.38. Now we can run the code again. And you can see that, oops, really, this wall is blue. Okay, so maybe the parameters have to be adjusted slightly better. Never expected that to happen. Okay, I'll rotate the camera, hope it helps. So, no, okay. Let's retune the filters. So I'm going to copy these parameters. Where are they? These parameters as the default values in the detector. Yeah, have to delete that. Never expected this objects to appear in the frame, but seems like when I'm moving my hand over here, the parameters of the camera or the white balance or whatever it is adjusts so that the wall is now a cup. I was talking exactly about that. So here you can see that, well, the life is full of surprises. I was not intended to show you this. When I was preparing the seminar at home, it worked differently. And now in this exact environment with a different object, you can see that without some extra filtering or very precise tuning, we can encounter some side effects like this one. Well, what am I going to do? I'm going to try to tune this filter so that it will work even with my hand inside. Maybe we can do it. Well, that's kind of fine, I guess. At least the wall is not here. And nope. Get back. Nope, too strict. Well, okay. So now it's kind of fine. Let's check. No, it's not. Okay, here the criteria is slightly off. I mean, in our current script, it will be fine. And here, Yeah, that's okay. So now I'm going to transfer the... Wait, what? Excuse me. I have just killed the program with the tuned parameters. I have to do that once again, but that will be faster. So stick with us. We're going to tune this color-based filter. I'm going to raise this lower threshold, and I think we kind of get rid of this wall, right? Oh, that's too much. Okay, so it works. It works. I guess so. So I have to just move the lower threshold in the hue channel to 99. Yeah, finally. So let's check. The camera is in the 0, and the distance is... okay. Do I have to readjust it? Well, not really. It's kind of working already. So that's 31 centimeter, and it says 35. And it's 37. Okay, I can make it even better. Now it says 38, and in reality it's 40. So let me just slightly decrease the height. Yeah. Six. Okay, great. So you can see that as I'm moving this cup, the distance is... No. One more thing. We are neglecting the angle of inclination, okay? And if I'm placing the cup here, the object appears smaller. The thing is that as the cup is moving here, the angle, this one, is becoming greater and greater, and it affects the way in which the cup is presented to the camera. So this works only for distances that are big enough, like here, and it works up to a certain extent, let's say. The thing is that we have to use something that is preserved when we are moving the object. So the first way to deal with this is to place the camera precisely over here, horizontally. But still, well, you can clearly tell that up to a certain degree it's working. I mean, it's not perfect by any means, but it's very easy, and it's fine when you have long focal length cameras that are somewhere far, far away. But we are using not this method. We are using usually proper picture to real, proper pic to R. And if you're not satisfied with this result, that makes sense. I'm not satisfied with it as well. And I'm going to proceed to the better way of measuring distances. So what are we going to do now? We're going to proceed to this cell over here, and we have to copy the camera parameters, because down there they are the same as they were before. Well, they are almost the same, but still, just for consistency, let's use the most recent one, the ones that we have obtained during the calibration. And what happens here? Here we have our picture-to-real or pic-to-R method implemented. That's basically the formula that you can see in the slide. The y calculation with tangents and so on, x calculation, rotation matrix with the sines and cosines by hand. And that's it. So here we're reading the frames in the loop. We are detecting the object. I'm going to copy the color-based filter here. And here, what we are doing is we are calling this pic-to-R function. Remember that we have found out the value of the angle, the inclination angle of the camera. Well, it is equal to the angle of the flat chessboard in the camera frame subtracted from pi/2, from 90 degrees, and it's written over here. So it was 54, as we found out. Let it be 54. And let's familiarize ourselves with the rest of the parameters of the pic-to-R function. First of all, it's the matrix of intrinsic parameters. Here we are cutting it into all the things that we need. The next one is the alpha angle. It's the rotation angle, this one. We're going to set it to be equal to 0, but it will work anyway with any angle. We can just assume that this robot, since it has no neck, it will not rotate its neck. The beta angle is this angle of inclination. X and Y are the coordinates in the picture, and the height is the height of the robot that is was measured like this. So this is the height of the robot. And now, color-based filter parameters, those ones. Okay. Here, after we have detected an object, let it be greater than, let's say, 2,500, we are first drawing the bounding box, and then we are taking the lower midpoint of this bounding box, and later we are going to consider this to be the coordinates of the object. It's this point over here. So we are calling the pic-to-R and drawing the result. So let's run the code. And what do we see here? The detection algorithm says that the x coordinate that is measured to my side is almost 0, and the distance along y-axis is, it says, 30 centimeters. As I can tell, it's 28. Okay, let's move it. Now it's 40, and here it's 42, 43 almost. Here it's 50, and here is 53.5. That's the pic-to-R. It's 48, 45. It's working. 36, 38, up to certain adjustments and imprecisions, and the measuring device not being aligned completely. Up to certain little things here and there, it's working. And if I move this object aside, you can see that the y-coordinate is almost intact, and the x-coordinate, well, now it's minus 4 centimeters. Yeah, and it's kind of 4 centimeters. 4 centimeters, and the 0 is somewhere almost here. So this pic-to-R thing is working, and I would ask you to check the code, to try to play around with it. Let's briefly cover this last cell once again. What do we have here? In the loop, we have all the regular reading, processing, obtaining the mask. And if we find the object in the bounding box, we take the middle point at the bottom of the bounding box as the coordinates of the object. In the scene, it's over here. And using the trigonometry, we are calculating the x and y coordinates in the real world on the table of this object. How do we do that? We are doing that with the help of pick2r function, with an input of the matrix of intrinsic parameters of the camera, the alpha angle, this angle, which is set to be 0, the inclination angle of the main optical axis, that is over here in radians, the coordinates of the object in the frame, and the height of the robot or the setup. And here in the pick2r, we are doing the math that was described in the lecture. So that's the pick2r, and monocular robots use this kind of approach to find out the geometrical positions of the objects in their surrounding. Thank you.